Alright, I started recording. My name is Sachin Sampath. I'm a PhD student in Indian Institute of Science under Dr. Balaji Sundarajan, and my field of study is communication. I'm in the ECE department. More specifically, my research is in coded caching and private information retrieval using caches, mostly combining coding theory and the usefulness of caches together. And today I'll give a brief recap of what was done in the lectures in week 3, and then I'll solve a few problems regarding the same. Okay, let me share my notes with you guys. I'll share the screen. Okay, can everybody see my screen? Can someone confirm? Okay, I'll start with a brief recap of what you guys saw in the lecture videos. And if there is a doubt in any of these sections, then you can ask me directly when I go to those sections. We were looking into methods of minimizing a Boolean expression or a function. And one way is just using the laws of Boolean algebra or Boolean identities. And that is completely based on your intuition. So here's an example. We have the expression a b bar c bar plus a b bar c plus a b c bar plus a b c. The first two terms have a b bar in common, so we have taken that out, and we get c bar plus c into a b bar. And the last two terms have a b in common, so we have taken that out, so we get a b into c bar plus c. And we know from the identity that c bar plus c is 1, so this will reduce to ab bar plus ab. Now again we can take this a common and write it as a into b bar plus b, which is equal to a. So this is what you do when you want to minimize an expression using the Boolean identities or the Boolean laws of algebra. Another example, x plus y plus z into x bar plus y plus z. So one way to solve this is simply distributing the multiplication over addition. So you can write it as x into x bar plus y plus z plus y into x bar plus y plus z, and so on. and then you multiply out the terms and then you try to figure out what the expression ends up to be. But that is a very tedious process. As you can see, there are lots of terms and lots of and operations and or operations that you need to do. So there is a simpler way to solve this, which is you remember that in normal algebra, addition does not distribute over multiplication. Only multiplication distributes over addition. And by that what I mean is, if you are taking multiplication and addition, then a into a into b plus c would simply be a into b plus a into c. But this is not true in the other order. That is, a plus b into c is not equal to a plus b into a plus c in normal algebra. If this is normal addition and multiplication, you can easily verify. You take numbers and see 2 plus 3 into 4 is 2 plus 12 is 14, but uh, 2 plus 3 into 2 plus 4 is 5 into 6, which is 30. So addition does not distribute over multiplication in normal algebra. But that is not the case in Boolean algebra. In Boolean algebra, this addition or the OR operation will distribute over the AND operation. So you can write a plus bc as a plus b into a plus c. Now in this above expression, you can take y plus z to be equal to a and x to be equal to b and x bar to be equal to c, and you substitute in this above identity. Okay. Um, so what you will get is y plus z plus x bar, which is nothing but y plus z, since x bar is 1. Oh no, 0. So that's an easier way to do than writing out all the terms here. It can be shown in this other example also. In the lecture video, this was solved in a different way, but essentially it's the same method, only the steps are different. Here I would directly use that law that plus distributes over dot, and written a plus a bar b bar as a plus a bar into a plus b bar. We know that a plus a bar is 1, so this reduces to a plus b bar. Okay. Next we looked at k map. A k map is an easier method to minimize a Boolean expression. So in the algebraic method, there are no particular rules that you can use. There is no one standard way that you can minimize this expression, and you might also get confused over which terms to group together and which terms to take out as common. And there's no such problem when you minimize an expression using k-map. And when you use k-map to minimize, then you know that the end result will always be the minimal expression. But when you are trying to do algebraically, what you get in the end might not be the most simplest or minimal form of the expression. That's one more advantage of k-map. But the problem is you can't draw this k-map for a large number of variables. By 6, it will be very difficult. Usually people only do it up to 4. That's why if you look at your assignment questions, I don't think they are given any 5 variable k-maps. Have they given any such question? Has anybody attempted the assignment? Hello? You can hear me, right? Hello. Yeah, week 3 assignment. Have they given K maps with 5 variables? Okay, when you check, you can see that most of the question, yeah, they're given only up to 4 variables. 5 and 6 is very cumbersome and it's not that practical anyway. So, well, but for up to 4 variables, it is very useful. Even 6 variables you can do, it's just a tedious process. But more than that is very difficult. So, what you do in a K map, you write out all the min terms in the function that you have, or you can use the truth table, and the cells, each of the cells in the K map represent one min term, and if that min term is present in the function, then you write a 1 in that place, or in the truth table if you have a 1, you can put a 1 directly in the K map. And well, you've seen this in the lecture, so I won't explain too much about this. This is a example of how you could write the K map from just seeing the expression. You could see this expression and fill out the K map, or you could use the truth table also. Anything works. So what you do in the K map, you try to group terms together. Here it's a 2 variable K map, so there are only 4 cells. So you can make a maximum of, there can be a group of 4 cells where everything is 1. That's the maximum. Otherwise, you will get pairs. There are Prashant Anand. You're asking, there are two different questions, right? Uh, A plus A bar is 1. A plus A bar is 1 all the time. It doesn't matter on what value A has taken. So by looking at A plus A bar, you don't really get any information. If A is 0, A bar will be 1, you will get 0 plus 1. 0 or 1 is 1. If A is 1, A bar will be 0, you get 1 or 0 is 1. So you don't get any information about A by knowing A plus A bar is 1. Then which is correct? Uh, Second one is correct. AB plus AB whole bar is 1. Okay. So you want to know what the difference is between A bar, B bar and AB whole bar. Well, I'll show you. You can simply write the truth table and figure it out. No? So you have A, B, then you have A bar, B bar, A bar, B bar, and AB and AB complement. 0 0 0 1 1 0 1 1. These are the possible values that A and B can take. A can be 0, B can be 0, A can be 1, B can be 1. So there are 4 combinations of A and B simultaneously. A bar will be 1, B bar will be 1 0 1 0. A bar B bar will be 1 0 0 0. AB will be 0 0 0 1. AB complement will be 1110. You can look at these two, they're totally different, right? A bar B bar becomes 1 only when both A and B are 0, and for all other combinations of A and B, A bar B bar is 0. But AB whole bar becomes 0 only for one combination, that is both when A and B are 1. For all other combinations it becomes 1. Did you understand, Prashant Anand? Prashant, you can unmute yourself and speak, it's okay. You don't if you're not comfortable with typing, you can all of you can just unmute your mic and tell your question to me directly. Okay. Okay. uh, in lecture 12, okay, they have shown you a 4 variable k map, and like I said, each of the cells represents a min term, and corresponding to that min term you have some index value which is given by this number 000001, and the order of this number, you can see that it goes from 0 here to 1 to 3 and 2. 0 1 3 2, it's not 0 1 2 3. So this is called gray code. It's a type of code where this is 0, this is 1, and this is actually 2 in gray code, and this is 3. That's the pattern it follows. So here, if you form a pair, then you can eliminate one variable. If you form a quad, you can eliminate two variables, and from an octet you can eliminate three variables. We'll see a few examples later, or you can check out the lecture videos. A few examples have been solved. And when you're forming groups, you try to form octets as much as possible, and then quads, and then pairs, and then single cell. Okay, here we have a K map with there are 6 ones in this K map, and one quad has been formed and another pair has been formed. And you can see in this quad, uh, from C bar D bar to C bar D, D is changing from D bar to D, so that variable can be eliminated. And from A bar B bar to A bar B, this B bar is changing this B term is changing from B bar to B, so that can be eliminated. So this quad you can write it as A bar C bar. That's what I've written here. And then here there's a pair. Well, since there's a pair, I can write that as B bar is changing to B, so that gets eliminated. So it's A bar C D bar. Is that correct? Is there a problem here? Can somebody spot a problem? No. Can anybody else find what is wrong here? There's something wrong. No. This K map, it is actually folded. So what that means is, if you cut out the sheet of paper, so if this K map, you write it here, write all the terms here. Then you can roll it like this. When you roll it like that, what happens? This edge and this edge are adjacent, right? So when you pluck it out, this corner that I'm showing and this corner, they're actually adjacent. That's what it means by a K map is foldable. So this cell and this cell are actually considered adjacent. Similarly, this cell and this cell are considered adjacent. That's why what you can do here is take these four as one group. Since this is adjacent to this and this is adjacent to this, you can form a group of four. Okay, and from that group of four, you can eliminate. See here, one in this column you have C bar D bar. In this column you have C D bar. So C bar is changing, D bar remains the same. So D bar remains as is. And in this row, you have A bar B bar. This row you have A bar B. B is changing from B bar to B, so that gets eliminated. You are left with A bar. So it's actually A bar C bar plus A bar D bar. That's the expression. Did you understand? Is there any confusion in grouping of cells? Well, if you forget that it is folded, then you might form wrong groups and then you'll get a wrong result. So always remember that there is the K map is folded. That is, the corner cells are adjacent to each other from left to right and from top to bottom. Okay. There are some more rules that you need to follow when grouping things in a K map. Uh, when there are redundant terms, keep the least number of groups possible. So here you can see this is also a group, right? It's a pair, and this is also a group. That's also a pair. You could form a group like this. You can form a group like this. Uh, I've admitted everybody. It doesn't show anyone. Well, it doesn't show anyone who is requesting to join. You can tell him to join again. Leave and try to join again, and I'm admitting everybody. I am not. As long as they wait for a few seconds, I'll admit. Okay, like I was saying, there are various ways in which you can form groups, but that doesn't mean you take all the groups. The main objective is to cover every single one that is in this group, and you do it with the least number of groups possible. So here you can do it with two groups that are shown here. So you take only two. If there are more groups, you just ignore them. That's what it means. That's what I mean when I said that redundant. It should be redundant groups. Is your friend Abhay Kumar? Okay, I've admitted him to the call. Okay. Second point about these K-maps is that more than one solution is possible. That is, when you are grouping, there might be different ways of forming these groups. But as long as you follow all the rules properly, then whatever expression you get is minimal. And even if the expressions look different, at the end of the day, they're all minimized forms. So you need to be careful with grouping. After that, you don't have to worry. And the examples that I showed and that were shown mostly in the usually we only deal with the sum of product forms. So this example, I'm taking the min terms and I'm writing down min terms for the minimized expression or the sum of product form, a bar d bar plus a bar c bar. That's SOP. But you could write it in terms of POS, product of sums. The changes that you need to do in that case is, instead of writing out these ones, you write down 0 everywhere. Okay, and then you form groups with these zeros. Here you could form a quad. This would be an octet. And the you have to write max terms in terms in instead of min terms in the uh, first column, first column and row, whatever index column and row. So this would be C plus D if you're writing in terms of product of sums, and this would be C plus D bar. And this would be C bar plus D bar. Well, the way we are getting this C bar is, if there's a 1 here, you write C bar. If there's a 1 here, then you write it as D bar. That is in POS. But in SOP, if there's a 1, you write it simply as C. You don't complement. And since there's a 1 in the second bit also, you write that as D. You don't complement it. So this is C bar plus D bar. And this is C bar plus D. Similarly here, A plus B, A plus B bar, A bar plus B bar, and A bar plus B. And now you observe this quad. In that quad, you come down the rows. A bar, here you have A bar, or here you have A and A, but then A is changing. You're getting A bar. So A is changing from A to A bar, and similarly with B also. B is also changing. B is going from B to B bar, and then B bar to B. So whatever literal or variable changes, that variable can be eliminated. So this quad will give you, if you look at the column, you have C bar plus D bar. That will give you the term C bar plus D bar. So what happened here? Like I said earlier, when you have a quad, two variables are eliminated. So A and B are gone. Now you look at this octet. There, if you look at the index of the column, C is changing from C to C bar, and here there is a change in the variable from D to D bar and then D bar to D. So both C and D are eliminated. On top of that, if you look at the rows, you have A bar in both these terms, but the second term is going from B bar to B. So even this B bar and B, this B term will be, or the variable B will be eliminated. So you get only A bar as the term for this octet, simplified term. So as you can see, the octet has eliminated three of the variables, C bar, D bar, C, B and D. Only A is left. So an octet will eliminate three variables. And this is the product of sums form for the same function. The function doesn't change, Only the way in which we are writing the expression has changed. Okay. Final exam, this product of sums, I am not sure. Probably not. Very less chance. Gate exam, they might ask. I don't know. If they ask, you should be able to do. They might not ask, but if they ask, you should know how to do it. Okay. Next, lecture 13. In this came up, huh? Tell me. It depends on department and program and which category you are in. I can't tell you a general. I don't know the. Uh, you should check previous year cutoff rankings. You can find, right. You can go on Google and see. For example, if you want to get VLSI, do you know VLSI in electronics? Then if you want to get into top IITs, IIT Bombay, Madras, or IISc, then you will have to have, if you are general category, then you need within 100 or 150 rank in your paper. Probably even less, maybe within 50 also. Because my rank was 170 something, and I didn't get VLSI. Gate exam, I I use mostly one or two books. That's all. And previous salt papers, whatever I could get, things like that. Video lecture. I didn't really see any video lecture, but I was reading notes from my college professors. Gate. I think. Huh. For what? I I am not sure if I can tell it to you like that, but I can only tell you what I use, but I can't give any guarantees. I solved a few mock tests in some website called AS or something. AS AS Engineering Academy. Yeah, AC AS. So I embedded. What do you mean by scope for jobs? I can't tell you what rank you need to get. I don't know. But if you are talking about job opportunities, then for embedded and VLSI and all, you'll have all. It will be good. You'll have more than other subjects, if that's what you're asking. If you want to do research also, then that is also fine. You'll have lots of opportunities. I think embedded, there is demand for embedded engineers and VLSI design engineers also. If you can get that department, DESC in IIC, I don't know in IITs which department that will be under, but embedded is a good subject. If you even communication and signal processing is also fine, or control engineering, that is also fine. Robotics, there's a robotics division in IISc, so these kinds of things will be fine. But if you want to do more research work, for research any subject is fine, but if you want to do something like quantum communication, then right now I don't think there are lots of jobs for that. Later in the future, when quantum stuff becomes better, then you might have more jobs. Right now there will be fewer jobs if you go for some niche subject like that. But embedded and VLSI, yeah, VLSI for jobs at least, VLSI is the best in terms of electronics. But electronics students also study VLSI if they want to. Electrical students? Uh, I didn't understand your question. I don't know which. Are you asking which institute is good for electrical students? There will be power systems engineering and stuff like that. You can go into power systems, power distribution systems. Mostly electrical students study that type of stuff, power related stuff. Animesh, no questions. I have not even started. Last time there were very few questions, right? So the session was over very early. Unfortunately, I have to conduct at least close to 2 hours. So I thought I will revise the topics that are done in the lecture. After that, I'll solve. I have 10 questions, 10 or 11 questions. I'll solve that. Any other questions? Anything related to the topic? Have you understood the lectures? Lecture 11 and 12 I revised right now, Animesh. Any doubts in that? No. Okay, lecture 13, don't care. Uh, See, in this K map, you have ones here. This is for SOP, you write out the ones and you ignore the other things. For POS, you would write out the zeros and ignore the other things. But these are only ones and zeros. There could be other entries that you can do in the K map. One such thing is a don't care condition. That means if you put, and it's denoted by an X. So if you put an X in this box here, that would mean that if you want to, you can take this X as 1. So here I could form a quad here, right? If that X was a 1. So I could take it as a 1. Or if I don't need it, I am just happy with whatever ones I have. Then I can ignore this X. I don't need to do anything with it. So that's called a don't care. How does this don't care come up? I have one example. From my college days, we did an experiment in the digital electronics lab. So have you seen a 7 segment display? You should have seen it in your calculators. This thing, that's called a 7 segment display. Why? There are 7 segments, that's why. See, this is one. I've labeled them A, B, C, D, F, G. 2, 3, 4, 5, 6, 7. So it's called a 7 segment display, and the way the experiment that we had is given here. You have a black box or an IC. Inside the IC, there are gates and other circuits. I don't go into the details. So How do they design the gates inside the circuit inside? What you do is these are the inputs A, B, C, D, and A, B, C, D can go from 0 to 9. Suppose you want to make a counter using this 7 segment display. So when you have A, B, C, D as 0, 0, 0, 0, or the decimal number 0, then you want this display to show you a 0. That means only A, B, C, D, E, F should light up and G should be dark. G should not turn on this LED. So that would show you a 0, right? And if I wanted a 1, you could give the input as 0001, and then from that input the circuit will do something and give uh, some output which are connected to these LEDs A, B, C, D, E, F. So if you want a 1, you want only B and C to turn on. Rest of the things must be off. So you could write this, whatever process is happening, whatever function that you want, in the form of a truth table like this. So when will this LED A be turned on? It will be on for the numbers 0. It won't be on for 1. It will be on for 2, 3. It will be off for 4. So you write out that combination. For 0, when it is on, it should be 1. For 1, this LED A will be off, so it is 0. But you can observe that this LED can only show up to the number 9, right? It can't show with one LED, you can't show 10. So whatever combination here, input combination you give for 10, that is 1010, that is 10, right? Okay, is it muted? Okay. You were able to hear what I was saying till now, right? Or do I need to repeat it? So here you have four inputs A, B, C, D. From A, B, C, D, you can think of this as forming binary numbers. So if A, B, C, D is 0, 0, 0, 0, that means you want to show 0 in the 7 segment display. So to show 0 in the 7 segment display, what you need to do is you need to light on the LEDs A, B, C, D, E, F. G must be off. So this you for different values of inputs for A, B, C, D, that is for different numbers, different LEDs must be turned on. And if you look at these LEDs, suppose you consider LED A, then this LED A should be turned on only when the number is 0 or 2 or 3. For the number 1, only B and C should be on, so A is off. And if you take off as 0, for the combination 0001, that is the number 1, A is off, so it is 0. Like that you write down the truth table, and at the end you come to numbers 10, 11, 12, 13, 14 up to 15. With 4 variables you can go up to 15, right? But what does 10 mean to this LED? If you have a single LED, you can't show 10 anyway. So you don't really care about what happens if someone gives the input as 10. That's how you get this don't care condition. So when the input sequence or the input variables are set to 1010, then A doesn't really care about that. Whether it is on or off, no one cares. So you can write A to be, you can take A as X. And when you are simplifying, you would fill up the corresponding cells as X. So here you can see um, this is 10, 11, 12, 13, 14, 15. These are all X's. And then you can group here. So if you take this X as 1, the one I erased just now, you can form a group of 4 that's acquired. and then you take the other x's as also 1, then you can form an octet. Anyway, there's an octet here. And then since the k-map is folded, you can consider a group in this way by taking these x's as ones. So that will give you a quad. So that's how don't cares could arise in practical situations. There might be other circuits, other reasons why you might not care about any particular a particular min term in this function. So this is just one reason. If you have access to a lab, you can later, once you finish this course, you can go out and try this experiment, and there will be other things, other experiments that I will tell you later that you could try out yourself. Okay, now I'll some terms were defined in the class. An implicant, uh, a term p is called an implicant of the Boolean expression if the expression takes the value 1 whenever p is 1. So if you have, say, this expression right here, a plus c plus bd, when a is 1, what will happen? 1 plus c plus bd, regardless of the values of b, c, d, a will be 1. So this term a can be taken as an it's called an implicant. Similarly, let's say bd is 1. For bd to be 1, b has to be 1 and d has to be 1. When bd is 1, you don't care about what happens to a and c. This function a will also be 1. So bd is an implicant. That way, this is not true for every particular uh, term, right? For example, if you have b is equal to 1, then a will become a plus c plus d. Now, a does not necessarily have to be 1. If a, c, d are all 0, then a will be 0. So this term b alone, it cannot be considered an implicant. Another example here would be, say, what will happen if you add one literal to any of these terms. Say you take BD and you write it as ABD. Is this an implicant? Can someone tell me if this will be an implicant? Why should all four variables be there? Uh, See, the minimized form of those blocks are called implicants, the term that you get. For example, here, if you take this quad, huh, that's an implicant, that group. But what does that group give you? You can write it in a minimized form also, right? This group can be written as B and D, that is BD. BD doesn't have A and C in it. Hmm. Vishwanathan, tell me what your doubt is. A variable itself is called a literal. A A is a huh. No, that's called a term. Here it will be a min term. A literal means a variable, okay? So this A, that's a literal. B, that's a literal. D, C, these are literals. Each block that represents a min term. So if you take this first box here, right, A, B, C, D is A bar, B bar, C bar, D bar is the first box. That is a min term. Right, that's not a literal. Ah, yeah, don't get confused by the naming. And each of these things, it's called a term. When it has all four literals, A, B, C, D, or A, B, C bar, D, then it's called a min term. So this is a min term. This is simply a term, and each of these variables is a literal. Got it? Ah. Now, an implicant does not need to be a min term. It doesn't need to have all four variables in it. An implicant can be just a single variable also. It can be any combination of the variables. It's only an implicant. It's called an implicant if whenever that implicant takes the value 1, then the function should also take a value 1. So ABD, take this. When will it be 1? Vishwanathan. No, when this particular term I'm showing in the, I'm marking with the circle, right? ABD. When will this term become 1? Ah, ah, when all three are 1, it will become 1, right? So A is equal to 1, B is equal to 1, D is equal to 1. This is the condition when ABD will become 1. But when B is equal to 1, D is equal to 1, BD will also be equal to 1, right? So, I am telling you, if A is 1, B is 1, D is 1. If A, if ABD has to be 1, if you want to make ABD is equal to 1, you have to make A is equal to 1, B is equal to 1, D is equal to 1, right? When you do that, BD will also be equal to 1, right? When BD is equal to 1, this entire function will be equal to 1 because you are adding other terms A, C, B bar, D bar to 1. It won't change it won't change. It will simply be 1, right? Boolean law 1 plus A, anything is 1. So whenever you want to make ABD 1, this A will also become 1. So ABD is an implicant. That is by definition. In the K map, if you want to find an implicant, you just see where you have ones and where you have groups of ones. So if you have a single one, that cell will represent an implicant. So wherever there is a 1, A bar, B bar, C bar, D bar, there is a 1 in the first cell. So A bar, B bar, C bar, D bar is an implicant. Then you can form an octet. You can see there's a octet that I have drawn at the bottom, the last two rows. When these two rows, they will simplify to A, the term A. So A is also a implicant. So from the K map, every cell where there is a 1 will be a implicant, and every pair, quad, octet, whatever group you can form, those will also give you implicants. But there are a special type of implicants called prime implicants. And where you I will explain with the K-map. It seems that that is easier for you guys to understand. So uh, in the K-map, an implicant is called a prime implicant if there is no bigger group that will cover that implicant. So for example, if you have in K-map somewhere, if you have 1111, then you can form a pair. This will be an implicant, but you could also form a quad, taking all four together. That will also be an implicant. But this pair is covered by the quad. So the pair is not a prime implicant, and the quad will be a prime implicant. Suppose there is another octet like this, where you have ones. So the quad is also an implicant. In this scenario, the octet is also an implicant. In this scenario, the quad won't be a prime implicant anymore. Only this octet is a prime implicant. Why? Because the quad is covered by the octet. So a prime implicant is an implicant that is not covered by a bigger group. And an essential prime implicant is a prime implicant that needs to be there when you're trying to minimize expressions in the K-map. So if you come across any problem where there are there will be multiple ways of choosing these implicants and prime implicants, right? So you try to minimize the number of groups that you have, and when you try to minimize the number of groups, whatever is left, those will be essential prime implicants. That's one way to understand it. Any doubt? Okay. So this is the general rule to form groups. You have to try to make as few groups as possible. The lesser number of groups that you have, the better. And you have to make as big, as large a group as possible. So each group should be as big as possible. You should cover more number of ones if you can. But you should also keep in mind that all the ones have to be covered at the end. Just because you want to make few groups, you can't leave out any of the ones. If there is a single one left somewhere and you can't really form a pair or quad, you just have to take the single one separately. That's the general rule. Next, okay, we got the truth table, we have this minimize expression, but what is the use? Where will you use it? This is just all mathematical, right? The use would be in building circuits like this. So you label these inputs as A, B, C, D, and you label these outputs as small a, b, c, d, e, f, g. And inside you have some kind of circuit. And what the circuit should do is take these inputs, and according to the truth table, the output should be high only when the uh, term, for example, if you take LED A should be 1 only when certain combinations of inputs are given. So the way you build those circuits is using these small elementary uh, circuit elements called gates. Why is it called a gate? Does anyone know? Well, these engineers and scientists, they're not that creative. So yeah, it's just like a physical gate. And so they called it a gate. That's all. You can see names like these a lot of times. If you have a circuit to count, it's just called a counter. And if it counts sequentially, it's called a sequential counter. That's the type of stuff. Okay, this is a circuit that does very basic Boolean operations. So there's A and B. Uh, you've seen in the lecture. An AND gate will be high only when both the inputs are high. An OR gate will be high when at least one of the inputs are high. And if both inputs are high, then also there's no problem. The output will be high. NOT gate will just invert whatever input you give. If you give 0, you will get a 1. If you give 1, you will get a 0. Buffer, why is a buffer used? It is just giving the same output as the input, right? Does anyone know why buffers are used? To provide delay. That is one use. Yeah, you can use for delays. You can also use for isolating two circuits. Suppose you have a very high powered circuit on one side and you have a very sensitive circuit on the other side. Uh, in that case, you don't want changes in power or current in one side of the circuit to disturb the other circuit, right? Suppose you have on one side you are dealing with 5 volts current and 5 amperes, uh, and on the other side you are dealing with this 5 millivolt circuit. So if there is some mistake with the 5-volt circuit and some current passes through to the 5 millivolt circuit, then that smaller power circuit will just burn out. So you can use a buffer in between in those cases. Huh? Huh? You would put a transformer inside your computer. How will you do that? This buffer is for digital circuits. It's a digital buffer. Uh, it's not a general buffer. This is only used when you are dealing with logic gates. So, hello. Uh, Hello. Can you hear me? There was a power cut. So, wait for 1 minute. I'll connect my tablet to the hotspot. Okay. This buffer can be used in different circuits in different ways. So, where is it? Did I stop sharing? 1 minute. Okay. That's a buffer circuit, and then we have a NAND gate. So NAND gate is an AND gate followed by a NOT gate. So it's it's a short form of NOT AND. So you do AND and then you do a NOT. You can hear me, right? And then you have a NOR gate, which is a NOT OR, an XOR gate, which is exclusive OR. So when exclusively one of the inputs is 1, then you will get the output as 1. That's why it's an exclusive OR gate. XNOR is just the complement of XOR gate. So when all the inputs are the same, then you'll get a 1. Or you could also think of this as in another way in many circuits. Uh, what we see XOR gate as is it counts how many ones there are in the circuit. So if there are an odd number of ones, then the output will be a 1. If there are an even number of ones, then the output will be a 0. So it's an odd checker, odd parity checker. That is used in something called error control coding. Maybe some places in computer science also they use that, a parity checking. And XNOR, it will count. It will give you a 1 if there are even number of ones. So you can see there are 0 ones. 0 is an even number. So here in the first input combination you get 1, and here there are 2 ones. So your output is 1. That's actually one use of these gates. Okay, and the symbols for XOR is a plus inside a circle. That's the symbol for XOR. And if you write out the expression, it will be a bar b plus ab bar. It is more convenient to remember this expression than this symbol, because this symbol doesn't tell you what it actually is, right? This one, this will tell you what is actually going on with the circuit. Okay. Combinational logic. Combinational logic is just forming functions where the output of the function just only depends on the input at some particular time. So it doesn't depend on the previous value. Suppose you are building a circuit, you'll see it later called a counter, where you want to count from 0 to 15. Say you're going from 0, 1, 2, 3, 4, 5. There in those circuits, if you want to go from 1 to 2, the circuit must know that it is currently at the state 1, right? If it wants to go to 2. If it doesn't know what state it currently is in, then how can it count upwards? So that circuit would be a sequential circuit where the output will depend on the previous values of the input, but we will see that later. And you saw how we can write out the circuit from the expression, and from the circuit you can also write out the expression. uh, from the expression you can form the circuit different ways. There is one point here, you see this dot, can you see it? here, this point. Oops. There, that dot means that there's a connection between those two wires. So as I've shown below, if there is no dot in between these two wires, that means there is no connection between those wires. Those wires are just passing one over the other. But if there is a dot, it means these two wires are connected at that point. So the voltage will be same in those wires. Uh, then among these gates, NAND and OR are called universal gates because any other gate can be realized. We say a realization when we want to implement something. So if there is some expression that we want, and then some circuit will actually implement that expression, then we can say that that's a realization of that expression. So using NAND and NOR gates, we can realize any other gates, and as long as you can realize AND or not, you should be able to implement any boolean expression in a circuit form. So this you have seen in class. Just for fun, you can try making XOR gate from only NAND gates. You can try it out yourself. If you don't get it, you can simply search on Google. You should be able to find it. And then try to analyze each of these nodes. Here you have written, right? From A, you got A bar, and from B, you get B bar here. And then that will give you A bar into B bar whole bar. Right? Like that. Even if you can't write the circuit for XOR from NAND, just see online, and then at each point you write out the expression and check whether that circuit that they have given is correct. Okay, so universal gates as such are only NAND and NOR, but if you take sets of gates, then also you may be able to achieve all possible Boolean expressions. For example, XOR and AND gate, XOR and OR gate you have seen in class. Okay, that's the revision. Now the remaining time I'll solve 10 or 11 problems. I am supposed to solve 15 problems, but some of the problems that I was given actually overlap with your current week assignment, week 3 assignment. So I can't tell you the answers for those things. Okay, the Boolean function f of ABC is equal to sigma 3467. Sigma means it's a sum of product form. 3467 will be the min terms. Is equivalent to. How would you solve this? You write out the K map for this. So here you'll get A bar terms, here you'll get A terms. This is B bar, C bar, B bar, C, B, C, B, C bar. And in terms of numbers, this will be 0, 1, 3, 2, 4, 5, 7, 6. You can see A bar, B bar, C bar is 0, 0, 0, which will be 0. A bar, B bar, C is 0, 0, 1, which will be 1. A bar, B, C is 0, 1, 1, 3. So if you remember this order of numbers, then when they give you the sum of expression form in terms of numbers, you can directly fill it up. So you have a 1 at 3, 4, 6 and 7. Now this one is isolated. You can't form there is only one way to form a group with this one, that is this pair. There are no other adjacent ones. For this one, you can form other pairs also. There's already formed pair is there, and then you could form a pair like this. But again, you can see here, for this one you have to form this pair. Now you already have two pairs and all the ones are covered. That's why you don't bother with adding the third pair that you could get. That would be the case if you're minimizing this expression, but they haven't really asked us to minimize the expression. They've asked us which of these functions is equivalent. So since you can see from the options that there are three terms, maybe you need to form all three pairs and see what the expression is. So what is the expression at the end? Here if you take this pair, then a bar and a is changing, so you will be left with bc, plus if you take this pair, here you have a c bar but b is changing to b bar, so b will get eliminated, that is a c bar, plus this third pair, that is ab, and if you look at the options, that is option c. You can rearrange this ab plus bc plus ac bar. So you have to, K-map is useful not only for minimization. You can write equivalent terms like this. You need not always minimize to the simplest form. For example, if for some reason you needed to use only two input gates everywhere, and then it would be beneficial to have all the terms have two symbols, right? I don't know. I can't really think of a reason why you would want this type of expression, but whatever. It's C. Yes, Asharani. It's C. Okay, what about second question? Will you try? I'll give you 2 minutes or 1 minute. This is also similar. You have to write the K map. I'll write the K map and you can try forming groups and simplifying it. So here you'll have A bar and A, B bar, C bar, B bar, C, B C, B C bar. And it'll be, this is 0, this is 2, this is 4, 5 and 6. A. Okay, let's see how to do this. Here this one, there's only one way you can form a group. You have to pair these, and then for this one you could form pairs like this and pairs like this. Is that right? Is that right, Animesh? Is the grouping that I have done correct here? Yes, I told in the earlier revision time, right? This map is folded, so like Animesh said, you can form a quad like this, and this quad will give you the simplified term. A will get eliminated, C bar will get eliminated, no, B will get eliminated, so C bar is the only thing left. So that quad gives you C bar, and just from C bar you can see, if you check the options, you will know that it is option A. But if it is not a multiple choice question, then you'll have to write the other term also, which is A, and C bar changes to C in this pair, so C gets eliminated, A B bar. That is option A. Okay, now he has given a function, and he has given a few terms, four terms: A bar C D bar, A B C D, A bar B C, and A bar B bar C bar D. Now, of these four terms, he wants to know which of these is not a prime implicant. So, which of them are not prime implicants? And you have four options. Would you like to try? Try this one. Only Asha Rani has tried first two questions. How about others? Try the third one. It's not too difficult. And it's a kind of practice. It'll help you solve your assignment questions faster. It'll also be good practice for your exams. Okay, an easy way to get your implicants and prime implicants is by writing the K-map. You can solve this question without writing the K-map also. Just by using the definition of implicants and prime implicants, you can think out which of these are prime implicants or not. For example, you have ABC, right? So ABC is a implicant, and ABCD will also have to be an implicant, because when ABCD is 1, ABC will be 1, and when ABC is 1, F will be 1. So by definition, ABCD is an implicant. Is it a prime implicant? No, because the definition, the way you do it by definition is, an implicant is a prime implicant if uh, removing these literals will not give you a non-implicant. So that means from ABCD, if you remove any of those literals, if you remove A, B, C, or you remove a combination of those, then whatever you get, that should also be an implicant. But you can see here, if you remove A, B, C, you will get D. D is not an implicant of this. Whenever D is 1, F need not be 1. So D is not an implicant. That means this ABCD is not a prime implicant. That is the definition way of doing it, just by using definitions. But that is harder to think of. The easier method would be to write down the K-map and form groups. We'll do the easy method. What is the K-map for this? This is a 4 variable K-map, so there are 16 cells. This will be A bar B bar, A bar B A B, A B bar. This will be C bar D bar, C bar D, C D, and C D bar. One minute, I'll connect back to my Wi-Fi. Okay. Um, and here, this is the function. I'll write it out so that it's visible. Okay, A, B bar, C bar. Which one is that? This is A, B bar, right? And C bar you have in two places. Here also you have C bar, here also you have C bar. So you have to fill one in both those places. Then A, B, C. This is A, B. And here you have a C and a C here. So these two will be 1. And A bar BC, this is A bar B. Again, C is here, so these two will be 1. And last term is A bar B bar D bar. This is A bar B bar. And you have one D bar here and one D bar here. So this is the K map for this function. Okay, no one has solved it. Fine, I'll only do it. You can form a quad and then you can form a pair like this, another pair, this is a pair, this is a pair. Well, those are all implicants, and there are many more implicants also. You can form this one as an implicant, this one as an implicant. But let's see. This quad will give you BC, right? It's A bar C D bar. A bar C D bar. That's this fellow. That's an implicant. Um, this is A bar C D bar. Then you have A B C D. That is A B C D. Then you have A bar B C. A bar B C. That's an implicant. A bar B C. And A bar B bar C bar D. A bar B bar C bar D. That's not an implicant at all. This one. There's no one. So right from that you can see that A bar B bar C bar D is not an implicant, so it could not be a prime implicant. So this is not a prime implicant, not Pi. And A bar B C. You can see that this A bar B C, this pair is inside a quad. So that's not a prime implicant, not Pi. A B C D. A B C D is this one, that's also inside a quad. You could even form a pair. So there are larger groups covering it, so that's not a Pi. And A bar C D bar. A bar C D bar is this one. There are no larger groups covering it, so that is a prime implicant. So this is a Pi. Is there any option here that says this? A says 1 and 3 are not. Here there are which are not prime implicant. So A means 1 and 3 are not Pi. But actually 1 is a Pi. So it's not A. B says 2 and 4 only. But 3 is also not a Pi. So it's not B. C says 1 and 2 only. 1 is a Pi. So it's not D. So the correct answer is none of the above. Okay. Next question. Consider the following min-term expression for f. The min terms 2, 7, 8 and 13 are don't care terms. The minimal SOP form of f is. I'll write the K-map, you guys also try it out yourself. You guys do the grouping at least. P bar Q bar, P bar Q, PQ, PQ bar, R bar S bar, R bar S, RS, RS bar. This will be 0, 1, 3, 2, 4, 5, 7, 6, and this one is what? 10, 13, 15, 14, 8, 9, 11, 10. 2, 7, 8 and 13 are don't cares. So these are don't cares. 2, 7, 8, 13. And the rest of the terms are 0, 5, 10 and 15. So 0, 5, 10 and 15. Okay. How will you form the groups? Uh, yeah, right. This is a quad. You can take the two x's as 1 and this is a quad. So here two quads. Quads will eliminate two variables. So you will get only terms with two variables. 2 out of 4 will be eliminated. So it can't be option C and D just from that. You don't even need to simplify. It should be one of A and B. B. Okay. The central quad Q is not changing, so that will give you a Q. Here S is not changing, so that will be S, QS. And the corner point quad, here Q bar is not changing. We have P bar, Q bar and PQ bar, so Q bar is not changing. And if you look at the column indices, then R bar, S bar and RS bar. R is changing from R bar to R. S is not changing, so it's S bar. So that's option B. Okay. Next, here you have a question on product of sums. So when you're writing the K map, you have to write out the zeros instead of ones, and the cells will represent max terms instead of min terms, so you have to be careful while writing that. So this will be 0, 0, 0, 1, 1, 1, 1, 0. And in terms of max terms, that will be C plus D, C plus D bar, C bar plus D bar, and C bar plus D. Here again 0, 0, 0, 1, 1, 1, 1, 0. That will be A plus B, A plus B bar, A bar plus B bar, and A bar plus B. Okay, now you have to fill out zeros wherever the indices are given. So 3, 4, 5, 6, all those are zeros. Option C. It's not option C. No, these are the zeros. So this 0 you can form a quad to cover that. To cover this 0 you can form a quad like this, and then to cover these 0. Who was that? Vishwanathan, na? A. Yes, yes, A is correct. Animesh, here the first quad I formed, the vertical quad. It has C bar plus D bar, right? 1 column, C bar plus D bar. So this quad. And since it's a quad, it will eliminate the other variables. A will go to A bar and B is changing to B bar. So A and B are both eliminated. So that is C bar plus D bar. Uh, so this thing is C plus D bar. So it's not option C. Right from that we can tell. Maybe you made a mistake while writing the index, or maybe grouping was different, or maybe you wrote down the zeros in a different way. It's alright. At least you tried. The second quad we have is this one. That will give you A plus B bar. So this one, these two have A plus B bar. This one has C bar plus D bar, so it's option A. Remaining term will be this quad. That's actually A bar plus C bar. Here B is changing, so B is eliminated here. D is changing, so D is eliminated. You get A bar plus C bar. So it's option A. Animesh, is there a problem here? No? Okay then. Question number 6. Um, F1 is product of 0456. So they're given pi, so it's POS form. F2 is pi 03467. The max term expansion for F1 and F2 is given by. So it's F1 and F2. What is F1? It's a product, but we call it a product, but it's not a product in the normal algebraic sense. It's a Boolean product, and in Boolean algebra, product is an AND operation. So you're actually ANDing the max terms 0456 in F1. So it's F1 is M0, M4, M5, M6, and F2 is similarly M0, M3, M4, M6, M7. F1 and F2 is M0, M4, M5, M6, and these are also actually ANDs, and you get M0, 3, M4, M6, M7. C is it? Yeah. So M0 you have got it twice, and by the idempotent law or whatever law it's called, A and A is A. So you can write it only once. The common terms you can write it only once. So you can write M6 and then you have M5, M7. This looks like a product of max terms, right? So this could be written as pi m of 0. There is a 3 also somewhere. Okay, 3. 0, 3, 4, 5, 6, 7. Which is option C. Hmm. 3 is there. 3 is there in second F2. Ah. Um, no. That's not how it works. It's not intersection. It is AND. Or it is a product. See, and is intersection when you give it values. When you're adding terms, then that doesn't mean you are intersecting those terms. You do understand? When you write and, you have a and b, you do a and b. Okay. No. Yeah. I've written down that right. It's F1. It's a product of these max terms M0, M4, M5, M6. F2 is product of these terms M0, M3, M4, M6, M7. And then you are taking a product of F1 and F2. So you are multiplying those two terms. Hmm. Ah. Then M3 should be there. Oh no. Yeah. When you give values to M3 and other terms, right? M3 and say which one is only present in one of them, M5. M5 is in F1, it is not in F2. So what happens uh, if M5 goes to 0, then that means F1 is 0. That should mean that F1 and F2 should also be 0, right? Ah, in max terms, you are doing the product of terms. So M0 is uh, you have gone up to 7. We can do that with only 3 variables. So M0 is A plus B plus C. M4 is A plus B bar plus C bar. This is what I'm writing. F1 is equal to. You can write it out. No, it's A bar plus B plus C and A bar plus B plus C bar. That is M5 and M6 is A bar plus B bar plus C. So if you have one term like this F1, F2 will also be products of this form. They are multiplied. And when you multiply these two together, F1 and F2, you are multiplying these max terms. So they won't get cancelled out. They need not be present in any in both of the terms. If it's present in one of them, that's enough. You can think of it. See, when you have A and B, then that means this will give you 1 only when A and B both are 1. In that sense, it's kind of like an intersection only. But it's not exactly an intersection operation that you're doing. It's a logic operation. So that's not how it works. Did you understand, or is there still a doubt? No, if you haven't understood, I can explain again. It's fine, right? Okay. Question number 7. Convert the SOP function to POS form. Again, write on the K-map. X bar X, Y bar Z bar, Y bar Z, Y Z, Y Z bar. So first time x bar, y bar, z bar is 1. X, y bar, z bar is this one. X, y, z bar is there. X bar, y, z bar is this one. X, y, z is this one. So if you want the POS form, you have to take the zeros. You have 3 zeros here, and you have to write out max terms. This will be y plus z. This will be y plus z bar, y bar plus z bar. This will be y bar plus z, and here this will be x. This will be x bar. Now you can see from the options that there are two terms. So, but there are 3 zeros, so you can do grouping. You can group these two and group these two, and this one will give you x plus z, x plus z bar, and this one will give you y plus z bar. Option C. Yes, you're right, Vishwanathan. It's option C. Okay, this is very simple. You can simply, you don't need to write anything out. Which logic gate is this? C. What about others? Vishwanathan, what do you think? Think it's R? Asha, what is it? You've been answering questions. What do you think it is? And. Shravani says it's and. Okay, this one is a NOT gate. So A will give A followed by a NOT gate will give you output as A complement. And this is also a NOT gate, so you get B complement. This is a NOR gate, and the inputs are A bar and B bar. For NOR gate, what you can do is, if it's difficult to remember what NOR does, you can simply put an OR gate and then a NOT gate. So you have A bar or B bar here, and then you have to complement that A bar or B bar whole bar, which is from De Morgan's law, A into B, A and B. So it's option C. Try out the next one. Vishal, it's AND gate. It's not NOR gate. Asha also. Is there a confusion here? If there's something wrong, you can ask. You got it? What about Vishal? Any confusion here, Vishal? Okay. Try out the next one. D, yeah? Okay. What about others? Yes. Here the symbol it's ground. Ground is at 0 watts generally. Well, they could you could use other volts also, but we take this grounding as 0 volts. So 0 volts would mean in a digital circuit as input 0 if it's positive logic. If we are using a negative logic circuit, then a 0 volts could mean a value high, so it could mean 1, but they have not mentioned anything, so we'll assume it is positive logic. So 0 volts, whatever ground they have given, that is logic low or 0. uh, A XNOR 0. Earlier I had shown you the expression for X NOR. So if C is the output of an X NOR gate and A and B are the inputs, X NOR is written in this way, and this is nothing but AB plus A bar B bar. So one of them, let's say B is equal to 0, you will get C is equal to A dot 0 plus A bar dot 0 bar. What is 0 bar? 0 bar is 1, and A dot 0 is 0. 0 plus A bar dot 1, which is nothing but A bar. So it's option D. Okay, question number 10. Minimization. They have given you the K-map themselves. You just need to group and minimize. How will you form the group? From the options you can see that there are two terms in each of them, so you should probably get two groups. B a, let's see. You could. This one is. This one has only one neighbor. This the one above. So you group those two together. This one also has only one neighbor, the one next to it. So you group those two together, and so all ones are covered. You take these two terms. If you write out the variables here, this is x bar, this is x, so y bar, z bar, y bar, z, y z bar. So this term is, what is it? This term is x bar, y bar, and this term will give you yz. So it is option B, like all the students have said. Okay, you have understood why this elimination happens in pairs, quads, and octets, right? Or is there anyone who doesn't know? See, consider a pair. Let me mark it with a different color. You take this pair. There are two ones in that, right? You write those two terms. You have x bar yz. That is this one. You have plus xyz. That is this one. Xyz. So here this term is common for both of them. So in a column, in this particular column, yz is same for both these ones. Only x is changing from x bar to x. So you take the yz out, you will get x bar plus x. So this is yz into 1, which is yz. Suppose you had a, let's see, some example, if you have a quad somewhere. Here you have a quad. That's a POS term. Let's not go to POS. Okay, here you have a quad. What does this quad mean? If you take all these as x's also, these don't cares also as 1, then these terms are PQ R bar S plus PQ R S plus P bar Q R bar S plus P bar Q R S. So in the first two terms, you can take PQ as common, you'll get R bar plus R. In the next two terms, you can take P bar Q as common, you'll get again R bar plus R. So that is uh, these two terms and these two terms. So r bar plus r is 1, you will get pqs plus p bar qs. Now again ps you can take common. No, qs you can take common, you'll get p plus p bar, which is nothing but qs. So that's how these variables get eliminated in a pair and a quad. If you write out those terms, you can actually algebraically do it. But instead of writing all these steps, you can simply say that in a pair, the term that is changing. See here, r bar is r term is changing from r bar to r, so that is the one which got eliminated. Again, p term is changing from p to p bar here, so p is the one which got eliminated. That's how this elimination happens in a K map. I hope everybody understood that part. Okay, we have one more question. In the sum of products function xyz is sigma 2345, the prime implicants are. K map with 3 variables, 8 cells. This is x bar x, this is y bar z bar y bar z, yz bar, 0 1 3 2 4 5 7 6 2 3 4 5 are ones. You group these two together, you group these two together, because so this one has only one adjacent. The one in the block 3 has only the one in block 2 as adjacent, so you have to take that group. And 4 and 5, those have only those themselves as adjacent ones, so you have to take that group. From these two groups you get well, that's pretty much the only grouping possible, so those are the only prime implicants that there are. You can't form a quad or octet to cover any of these. And this prime implicant is x bar y, this would be xy bar, so it's option A. Okay, that's pretty much it. I had one more question, right? Writing XOR from NAND. So you want what is XOR? C is the output and A and B are the inputs. XOR is A bar B plus A B bar. So this is a circuit. I just remember it. That's a. I didn't come up with on the spot. So you have A. You get A bar from that, and B. You get B bar, and then you get A bar into B bar whole bar, which is A plus B, and then you NAND this together, you'll get A bar into A plus B whole bar, which is A bar B complement, because A bar A is 0, which is A plus B bar. Similarly, you do for B bar also. And since this is kind of a symmetrical circuit, if this is A plus B bar, this will be A bar plus B. And then you take these two and put it through another NAND gate. What will you get? A plus B bar into A bar plus B whole bar, which is A bar is 0 plus AB plus a bar b bar plus b bar b is 0. So ab plus a bar b bar the whole bar is this. This thing is NAND. No, not NAND. That thing is XNOR. XNOR. Then you have a whole complement. So it is an XOR. So that's how you can get an XOR gate using only NAND gates. You can try other combinations yourself just for if you want to practice and you didn't get any good questions somewhere, then you can try writing these circuits yourself. You can try to get this XOR and XNOR from NOR gates instead of NAND gates. That could be one exercise. Okay, that's pretty much it for this session. This session, I think the revision part was too long. It took too much time, but I had fewer questions. Next time I'll try to find more questions and I'll try to cut down on the recap part. Okay.